Alright, welcome to Chapter 12, Problems Walkthrough for some of the questions at the end of Chapter 12, just to work on photovoltaic cells and some math. And so we're going to just do the photovoltaic questions that they have, so we'll do 16, 17, 18. So starting with question 16, if a commercial solar cell with a maximum output of 2 amps at 0.5 volts costs $30, what will be the cost of a photovoltaic plant at peak kilowatt? So 2 pieces of information, I wrote those down, is that an amp times a volt equals a watt, and that 1 kilowatt is equal to 1,000 watts. So the first step will be to do the 2 amps times the 0.5 volts, which will give me 1 watt. So we have the 2 amps times the 0.5 gives me 1 watt. The question asks for what will be the cost of a kilowatt. And so I only have 1 watt per solar panel, and each photovoltaic cell is giving me a $30 cost. And so I can do 1,000 of these, because each one is equal to 1 watt, so I need 1,000 of these plants, times my $30 per system. And when you times that up, that'll come out to be 30,000. That's pretty easy. They're logical with the exception of just that you needed to know amps times volts equals watts. So let's work on 17. All right, question 17. We have discussed a solar cell farm for the conversion of sunlight into electrical energy. If the solar cell used have an efficiency of 10%, what are the area of the land that is needed to produce the output of 1,000 megawatts? Assuming that means installation of a 500 megawatts per meter squared. All right, so we have a product that does 500 megawatts per meter squared, but its average efficiency is only 10%. So the first step is to find out my new efficiency. So that's going to be my 500 watts per meter squared times its efficiency of 10%, so 0.1, right? That's going to give me a 50 watt per meter squared. My next step will be to divide it by my 1,000 megawatt system. So for this, it'll be 1 to the power of 9, or another way to think of it will be to put in all my zeros, right? So I can do 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. I'm going to divide that by 50 watts, because I'm changing it to watts so that I can convert into watts, and meters squared. So watts and watts will cancel out, and I will get my quartered up number, which will be 2, 3, 4, 5, 6, 7. So 20,000 meters squared. So that would be my new answer, working on 17. All right, so let's work on 18. I'm going to clean up my board again. All right, so question 18, a commercially available solar cell model puts out 3 volts at 0.1 amperes and measures 5 centimeters by 8 centimeters. How large an array is necessary to provide an output of 40 watts? All right, so first step is let's figure out what the wattage of our actual cells are, which is going to be my amperes of 0.1 times my 3 volts, which gives me my 0.3 watts. These are like those little chips. This isn't much. Now, the size of these are also small, so let's find out the area. And that's 5 centimeters times 8 centimeters, which just gives me 40, and that's centimeters squared, cm squared, right? So that's the size. Each 0.3 watt product is 40 centimeters squared. So now I want to know how many centimeters in size will be a 40 watt system. So I'm going to take my 40 watts and divided that by my 0.3 so that I know how many of these little 40 centimeters squared things I need. And we get a repeating number, and I get 103.6 0.33333 repeating, so I'm going to put a 4 rounding up. And the watts canceled out, so I'm going to need 133.4 of these. And the size of them is 40 centimeters, so I'm going to take 133.4 times that by my 40 centimeters squared, and I'll get my total size of my product. And the unit is still going to be in centimeters squared. I'm going to round again, and I get 533.4 centimeters squared. So that's going to be the size to provide 40 watts of power on my solar cell. So those are questions 16, 17, and 18. Just a quick walkthrough. Just want to show you how to do them. As you can see, with the exception of this new equation of amps equals volts, or amps times volts equals watts, which is basically current times storage equals total power, right? That's what we're doing to get our answers. Other than that part of the equation, everything else is just kind of logic. You have to build up from the other math that you learned. All right, I hope this helps.